Alright, welcome back, guys. Today we're going to be continuing our discussion of the action potential. Last time we talked about how we can stimulate the cell to produce an action potential, and now we're going to talk about the actual, mechanism that the cell goes through. And last time we had mentioned, or we had brought up, this idea of voltage channels, voltage-gated channels. So just to summarize what voltage-gated channels are, they're just channels that permeate the membrane that allow for the passage of ions from the outside to the inside of the cell or vice versa. And this is done through a certain voltage input that is, induced by like an overall electrical, sensation that happens. And that entire, moving across the gradient, the entire ions moving across the gradient causes this action potential we're talking about, and the action potential causes a cellular signal, which is kind of like spread out, whether it be through like the local field of neurons, or it could even be in your peripheral nervous system and whatnot. So today we're going to talk specifically about sodium, and I think sodium is one of the more important ones. Sodium and potassium is one of the more important ones, but sodium is especially important because in the context of the action potential. So voltage-gated sodium channels are extremely dynamic, and these channels are more likely to open once voltage becomes more positive, or in other words, there's a depolarization occurring. Just reintroducing depolarization, if we have, this is the graph, that's not a good graph. If this is the graph, this is resting. A depolarization is just a movement upwards, until, an action potential happens. This is an action potential. I'm just going to label it AP. Put some dots there. Cool. So it's just, you see that it's becoming less negative over here, but it's also becoming more positive. So the movement towards more positive or less negative, or basically the rising phase of the action potential, is what causes sodium gates to open. So we can simulate these neurons through a certain patch of membrane. So there's a certain mismatch in a certain part of the membrane, which causes voltage to increase. And raising the voltage allows the sodium voltage channels to obviously open. And what's interesting is, once this opens, we see sodium moving across the gradient. Sodium is moving from, say it's outside of the cell, it's moving to the inside of the cell. And what's happening here is we're having voltage become more positive. And guess what we first, what was the first thing we said? Voltage-gated channels open when sodium voltage-gated channels open when there's an increase in the positivity of the membrane potential. So in that case, once sodium moves across the membrane, we see there is a further depolarization, or there's a further activation of these voltage-gated channels. And this is called a positive feedback loop. Basically, the stimulant causes an action to keep cascading instead of reversing the action to return it to, say, homeostasis. And so this is what, if you're looking at a graph of the action potential, say, this is the graph, we have a stimulation over here. So basically this is our input, signal. And then certainly we have this deep, rising phase. And this extra positive, polarization occurs because sodium channels keep on activating. They keep on becoming more permeable, and overall the ion sodium becomes more permeable to the membrane, which causes an increase in the positivity of the membrane potential. So, but what happens is, after a certain amount of time, the channels just become inactivated, or basically they close back up. And let me tell you why. We see that permeability is increasing, and if we look at the Nernst equation, let me just pull it up here. Say this is specifically for sodium. We have negative 60 log Na plus over Na plus, one of them is out and the other is in. If we have a permeability, let's just put that out here. A permeability of our sodium, if it's increasing, what's happening is that we are deviating from this equilibrium potential. So the more deviation we have from the equilibrium potential, the more the system wants to return back to equilibrium. So to once again reestablish that permeability that was, initially present in the system, all of the sodium channels inactivate just about around its equilibrium potential. So this would be E sub Na. Okay. So what happens after that? So this also makes us, this allows us to make an important assumption about, the peak of an action potential, which is, let me just scroll down here, which basically says that the max voltage across the membrane potential, or across the membrane, is also equal to the equilibrium potential of sodium, which is, like we mentioned before, 60 log of sodium, concentration of sodium going out over concentration of sodium going in. All right, so that kind of defines that, and we should also establish what is the equilibrium potential of sodium, and this has already previously been mentioned, but it's 55 millivolts, and soon to come we will talk about potassium, so we might as well mention that here. E potassium is equal to negative 77 millivolts. Okay, now you might be wondering, okay, I told you what E potassium is, but what is the relevance of that? Why does it matter? And this is what we're going to talk about. To reset the voltage of the membrane after the sodium flushes back in, potassium channels open. So here at this phase over here, we see potassium channels open, and now there's a permeability in the cell towards potassium. So the potassium channels open due to the positive potential, but they open at a very slower kinetic rate than do the sodium channels. So it's a very slow process, really, what's happening, and this is called the falling phase over here. This is when we don't see that sodium is open. There's no permeability of sodium, but there's increasing but slowly increasing permeability of potassium. And potassium keeps on. It brings the membrane potential back to its starting point. And why does it bring it back? Well, the flow of this positive, ion, potassium, is in the opposite direction of the flow of the previously positive ion, sodium. So what happens is the contracting movements of sodium and potassium allow the positive potential to drop back to the resting potential. And so it should stabilize at the resting potential. But remember what I said, potassium has a different kinetic rate than does sodium. And this also applies to how it might be inactivated or closed. It takes a longer time for for potassium to close back up. And what happens is, although it will reach the membrane potential or the resting potential, it closes very slowly. So for a certain portion, the potassium channels are still open, which causes a hyperpolarization of a certain extent. And this hyperpolarization is what we call the undershoot. So the explanation, once again, is, the potassium channels. They're extremely slow to activate, and they're also extremely slow to deactivate. And what happens now finally is we restabilize and come back to our resting potential. So that is the steps of the action potential, which we can just quickly sum up once again. So we have one, we're going to have the resting phase, and this is, the default of the neuron. Then we have the stimulation, which is kind of like, we're reaching that threshold current for something to actually happen. Then we have the rising phase, and this is where we see most of the sodium ion channels open and more of an electrochemical gradient favored with sodium occur. Eventually, we work up to the equilibrium potential of sodium, and at that point, we have a falling phase, which means that sodium permeability ceases and we start having more potassium permeability. And potassium has lower kinetics than whatever it's called. It has lower kinetics than sodium. Excuse me for my, my unfamiliar or my informalness. It's just like, it's been a long day. But because there's a slower kinetics of the potassium, we see an undershoot happen. And finally, we have the return or the restabilizing. So I'm just going to quickly graph this out and see if I'll try to color code it and see if you can go through, pause the video, and maybe just label it for yourself. So here we have our first thing. And then here we're going to have our second thing. Here we're going to have our third thing. Our fourth. And not finally. Fifth thing. And then finally sixth thing. So go ahead and pause the video, try to label this for yourself, see what do each of these colored areas represent, and if it's not showing on the screen here, I'll just quickly scroll down so that's shown. So pause the video, I'll give you a few seconds, and we'll come back. Alright, hopefully you paused the video, you've taken a look at this, and we're just going to quickly go through this. This is the resting phase, so the resting phase is in red. This is the stimulation, so this is the current that's being produced that just slightly gives it that, push to start rapidly depolarizing further. So this is this orange color. And then we have in this green color, we have the rising phase, we have those sodium ions being permeable. So this is in green. And then we have the falling phase in this magenta color. And this is where we have potassium ions being permeable. Undershoot is potassium ions are still permeable, and that is that blue color. And then finally we have this return, which is back towards the resting potential, which is in yellow. Alright, so hopefully this all made sense to you. Just wanted to let you know that my comment section for the YouTube videos are always open. If there are any questions on the material or any suggestions on how I could do better, how I can help anyone learn better, please, please, please do not hesitate to put those comments down below. Let me know how I did overall and what you would like to learn next. So next we're going to go further into the action potential. We're going to talk about absolute and relative refractory periods and hopefully get into some more potential propagation.